Okay. Okay. Starting. Are we going to start? Hmm? Yeah, come in, come in. Okay, I'm going to start now. Since everyone still like moves around and talks and stuff. So yeah, this is the strings day, the string algorithms. And basically the most interesting problem that's concerned with strings is the substring matching. When you have a text and you, for example, you want to find all occurrences of a word in the text, right? Like if you're looking at a page in the browser and you press Ctrl F and you're looking for a word and stuff. So you want to know how to do that fast. And there are quite a few ways to do that in quite a few different settings. We're going to talk about some ways that are non-trivial today, but still like probably not the best in some aspects. So I said that this is the most interesting problem because it gives rise to, I think, the most approaches that you have, but you can have a lot of different problems too. I hope that we will discuss some of them today. So, okay, we have a text S, right? So usually S is large. I don't know, this could be like, I don't know, the entire internet, okay? A very large text, or a very long book. So, I don't know, a few megabytes or something. And a template that we are looking for is usually small, but not always. It could be large as well, like maybe as large as the text itself. So there are a few cases. And okay, so we want to find all occurrences of T in S. So we want to, well, again, there are a few different settings. Maybe we just want to check if T is present in S, like at least once, right? So the answer is either yes or no. In other cases, we may want to determine all the positions so that if you start at this position and start reading, you will read the word T. Okay, so this is like you find all occurrences. And like the trivial algorithm to do that would be just naive matching. We try all possible positions and start reading. Okay, and see if it matches. Not very interesting. And the complexity is linear. You can see that it's proportional to the product of the length, right? Because in the worst case, we could, for every position, go like until the end of the template, and then maybe it fails. We don't know. So we want to do better than that, and there are a few ways. They are almost equivalent, but in order to solve a lot of problems efficiently, you need to know all of them. because sometimes one is more convenient than the other. So the first approach that we are going to discuss is something called Knut-Morris-Pratt algorithm. Or just KMP. And to define what it does, we need to define another thing, which is called prefix function. Or sometimes just P function. Okay, so it's a function. No, it's actually an array. If you have a string like this, so what do we mean by prefix function? Basically, we define the prefix function in each of the positions. Okay, so in the first position we set it to be 0, so this is P in each position. In every other position, like here, the prefix function is the largest number. Okay, so assume that we want to try if prefix function is 3. So what we do check is, so we consider this prefix here, and then we look at the first 3 characters, and we look at the last 3 characters. Okay, and we look if this matches, and it doesn't in this case. Okay, so it's ABA and ACA doesn't match. Like obviously we could take 5 and it would match, but it's not very interesting, so we don't take any numbers that are at least as large as the length of the prefix. So we take like the next smallest, right? Next largest. Okay. Well, it sounds kind of weird, maybe, because it's not really clear, like, how do we compute this thing fast enough, and it maybe it's not very clear what it has to do with substring matching. Seems kind of arbitrary, but let us still compute some values here. So here 0, here A and B doesn't match, so we have 0 as well. Right here, I think what do we have here? Yeah, it's 1. Here is 0. Yeah, basically for the value to be not 0, we have so that we should have that the characters are matching. Otherwise, it doesn't work. Why did I say that? That's completely incorrect. Like, I mean, if I was examining a student and he said that, I think I would just send him away. Okay, never mind. So here, I don't trust myself anymore. You tell me what you are here. Okay? Okay, 1. Here. Here. 3. Nice. Okay. So let's answer the second question. What does the prefix function, assuming that we are kind of able to compute it somehow faster than you would expect? So what does it have to do? What does it have to do with matching substrings? So okay, if you're able to compute prefix function, and we are looking for a template in the text here, how can we use prefix function to find it? And we do that by writing down another string, like auxiliary. It starts with T, then there is a character. There is a character that does not occur anywhere, and then we have the text. Okay. So what do we have now is, well, if we compute the prefix function of a string, and we look at the position that it takes here, and I will take another marker. Yeah, okay. never mind. So if you have the values that the prefix function has here, then they cannot exceed the length of t. Okay, because basically that would mean that we have matched this ugly character with something, but we cannot match it with anything. So all values here are between 0 and the length of t, and the marker is even worse. Okay. Well, yeah, that works. So the values here are between 0 and the length of t, and when we have a value equal to the length of t, then by definition of the prefix function we have a match between a t and the substrings that ends at the respective position. Okay, so assuming that we are able to count the prefix function of a string, then we can basically search for substrings in the same time we are computing prefix function. Okay. All right. So that's the Knut-Morris-Pratt algorithm, except for the part where we actually do any kind of useful work, that is compute prefix function. Let's talk about that. So, well, let's make a few observations, I guess. The first observation is that, well, if we have a string and we have the prefix function at the very last position here, okay, x. So here, if you have the next prefix function, maybe I should go like pi and pi plus 1, okay. So if we have these two consecutive values, then we always have that pi plus 1 does not exceed pi and plus 1. Okay, and the reason for that is that assume that, like, if you look at the match with that ends at the I plus 1th position here, then basically just deleting the last character here and here, we obtain a match that's only one character smaller. So that's the reason why we have this inequality. So our prefix function basically looks like it starts at 0, and then at some points it grows, but does not grow too fast. It grows at most one character, but at other times it may fall. It may fall to 0. You can guess where it falls. That is actually a useful fact because we will use it for estimating the complexity a bit later. So okay, let's try and think how should we compute the prefix function. We want to do that from left to right. So we want to use some previous values to compute something after that. How about we try and write b here and try to find out, like, okay, so the prefix function here would be 2. Okay. So okay, how can we logically conclude that the prefix function is 2? So okay, so the previous value of the prefix function was 3, right? And if you look at the match here, then if we want to increase it, we know that it increases sometimes. Then it only works if this correct character matches with the next one. Okay, but okay, it doesn't. So we have to look for some other options. And basically, what we are looking for is the next candidate match between the prefix and the suffix that we can have a shot at continuing. Okay, just like here, we tried to continue with the character, but it didn't work. Okay, so what we're looking for in this string here is for, okay, we tried this match between the prefix and the suffix and it didn't work. Okay, let's try the next one. And so, and like the next one would be these two characters A, right? Like if we try to gradually, like we tried match between prefix and suffix of length 2 and it doesn't work. Then we try the match between 1 and 1 and it works, and we also can continue that. So that's why we write 2 here. That's not exactly what we are going to do, but the essence of that is that we should look for all matches between prefix and the suffix, and out of that we should choose such a pair that we can continue it with the characters so that the next characters are a match, and out of that it's also the longest. Okay, make sense? All right. So now obviously if you try to match all pairs, that would take far too long, and we don't want to do that. So we want to make a few more observations. So okay, we have a string and we have this longest match of a prefix and a suffix, and that's exactly the previous value of the prefix function, right, by definition. So we look at that and suppose it doesn't work. So now we want to look at the next pair of prefix and the suffix, right? So in the string a prefix here and the suffix is here, but we also know that the previous ones do match, right? So in fact, if this suffix is here, right? So we had like, let's write it like this is a string, I don't know, okay, v, because these are equal, they should have matched, and this is u, and they also match. So we can see that u is simultaneously a prefix of v because it occurs here, and also a suffix of v because it occurs here. Okay. So we can see that u is like a match of a prefix and a suffix here in v. So, and also out of all these matches of the prefix and the suffix in v, it's also the longest, because we wanted to go for the longest match out of all the smallest, right? Can we, okay, so it's the largest match of a prefix and a suffix in v, which is a prefix. Can we somehow characterize this length, for example, length of u? Yes, this is exactly the prefix function in this position, just by definition. So what happens next is we try these. Okay, so despite the fact that we are taking the prefix function at this position, we still try to match the characters here. Okay, so okay, maybe it didn't match, maybe it did. If it did, then we continue. If it didn't, what do we have to do? Basically the same thing. We are going to continue our considering our matches between the prefix and the suffix, and by the same argument, the next thing that we are going to consider is the prefix function at the end of u. Okay, and so on. And what happens is either we find a match between the prefix and the suffix that we can continue, or we find that no match can be continued. In this case, the prefix function is 0. Okay? So let's try and write some code, I guess. So our characters, our string, let's say that there's a string s, and its characters are numbered from 0 to n-1, and we want to fill the array p. Okay, so the first thing that we do know is that p0 is 0 by definition, and so okay, p0 is the prefix function that ends right here at the 0th character. Like, so the index here is the actual index in the string, because sometimes he used the index as the number of characters. So this in fact corresponds to the prefix function of a single character rather than an empty string, just so you don't get confused. So now we are doing something like for I in 1 and minus 1. Okay, so what we're going to do is we are initializing our value of pi with the previous prefix function. So this is exactly the length of the block here. Okay, the length of the block here, and also quite conveniently the position of the character that we are going to match with the character I. Okay, so if the length is 1, right? Yes, so pi is length. The value is the length. So if length is 1, then conveniently the character after a block of length 1 is the first character in our numeration anyway. So now we are doing something like while. Basically, here we are going to iterate the prefix function until we arrive at a match. So what we are going to do is, so basically we are doing this while, I'll leave a space here, while si is not equal to spi. Okay, so here we do, so if this doesn't match, then we have to go to a smaller prefix, right? And let's figure out what that be. So our current value of pi points here, like on the first iteration it would point here. Okay, so where do we have to shift it? We have to take the prefix function of the previous character. Okay, so we move to the previous character and then take the prefix function. So we do something like pi equal to p of pi minus 1, like that. So do you think there are any problems with this cycle? Let's think about the case where we don't have a match at all. So what happens is pi eventually becomes 0, and here we will try to access the negative value. So in order to not do that, we will do this while pi is greater than 0. So when pi is 0, then there is not much that we can do. But there are still, like, so now after leaving this cycle, we have a certain block, right? That probably have matched, and probably these characters do coincide, but it's not guaranteed, because it could be that our prefix function is 0 and we have stopped because of this condition rather than because of this condition. So to make like easy work of all these cases, we are going to write if this condition holds, like if si is equal to spi, then we say that okay, we can increase pi by 1. And that's it. That's the whole code to compute the prefix function. Are there any questions about what does it mean? How does it work? Why does it work? Okay. So now let's try and figure out how long does it take to compute the prefix function, because there could be cases where a single iteration of this cycle, like this cycle is obviously the hardest part here. So there are cases where like this cycle takes a long time, because if we consider a string that consists of all a's, okay, then its prefix function must be increasing, and then we take a character b, for example, and what we are doing then is we try to take these prefix and this suffix and try to match them, but it doesn't work because a and b. So we go to the prefix function, but it only decreases by 1. and then it doesn't match as well. So we have to do like n iterations basically to understand the fact that it's 0 here. So this cycle can take a lot of time on any particular iteration, but the thing is, the total time it takes to perform everything here is linear. Is linear in the number of characters, and the way to see it is basically, well, let's look at the values of the prefix function. Okay, we can even draw like a graph of the prefix function. Okay, so it starts at 0. Sometimes it increases by 1, and sometimes it decreases, and you can see that it can decrease very rapidly, right? Then it increases again and again, and well, something like this. Okay, so let's consider like so which kind of changes do we have here? First of all, we have increases, right? And we have basically only n increases. Okay, so the first kind of changes we have to the prefix function are increases, and there are at most n increases, because on every single iteration there is only a single time that would happen. And we also have decreases, and we are not sure how many of them there are, but we know that the prefix function is never negative, so that must mean that the number of decreases should not increase the number of increases, because otherwise, since every decrease is basically it decreases by at least 1, right? If we had more decreases than increases, then we would like hit the floor and go to the negative, right? So that must mean that since increases there are almost at most n increases, that must mean that the number of decreases is almost at most n. So this is how we prove the fact that in total this cycle will be executed at most n times over all iterations here. Okay, so this is something that we usually call amortized analysis. And these words mean not too much, except that like they mean that if we have an algorithm that has several phases and we want to bound the total number of phases, the total complexity of all phases, but each particular phase could take long. Okay, so here we are looking at like the invariant, basically the value of the prefix function. So okay, my phone is off now. So yep, here how we match a substring in text with the prefix function. Are there any questions at this point? Okay. Let's move on to the next approach, which is kind of symmetrical, and that's what's called the Z function. So the Z function is basically a prefix function where like turn on its head. So what does it mean is if we have a string, we are still going to compute certain values for each position in the string, but it's going to mean something different. So the Z function of the first character doesn't exactly matter, but let's say that it's equal to the length of the string. Okay. If we choose any other character, like we could choose this one, the Z function is computed as follows. Basically, we compare these characters, and if they are not equal, then it's 0. Okay. If it's equal, then we move and compare the next one. So the Z function here is the largest length, so that the prefix and like the prefix of the suffix here, the substring that starts here coincides with the prefix of the corresponding length. Okay, so well, let's try and compute the z function now. So here we have we should have 0, I think, and that is the case where the characters doesn't match. You have 0. Okay, I was confused. All right, here it's, what do you think? It's 1. Here it doesn't match, it's 0. Here it should be 3 exactly. Here is 0. Here is 1. Okay. Yeah. So nice function. Let's assume that we can compute it and see how do we use it to actually, match some strings. And it's basically the same approach. We construct this string and compute that function, so that if we have a value of size of t here, then it means that it must be the start of a match. Okay. So the question is why we are doing like almost the same thing again, but once again you have to know all kinds of approaches, because there are a lot of problems that are concerned with strings, and basically you're going to encounter a lot of today. And in different contexts it is more convenient to use either basically z function or prefix function or something else, but these are basics, so it's good to know them. What was this? Yes, so we know how to match this using the z function, but we don't know how to compute it yet. Well, let's try and compute it, except that it will be slightly different. We will be we will keep track of one specific thing, and that thing is called the z block. Okay, so what does it mean exactly is, if we are at the position I, for example, so we have computed the z function up to this point. Okay, so we don't know its value here, but we know for all the smallest one. So for all of them, like we ignore the z function at the start, because it doesn't actually give us any information. But for all the others, we can look for these matches with the prefixes, and some of them are longer, some of them are shorter. So the z block is one of these substrings that have the greatest right endpoint. Okay, so out of all of these, we will choose these as the z block. Okay, so this is how we define it. And why do we do that? Basically, what we are going to do is we are going to take this substring and use this information, like the information that it matches with prefix, to shift around some information between these and this, pretty much like we used in the prefix function. And that will allow us to count some things. Well, so let's take a look here. So assume that we have a z block. Okay, so we live in the z block, and our I is probably somewhere inside, and that z block is matched with a prefix of the same length. So it's a prefix that starts at 0 and ends in r minus o, like that. So now we want to know what happens when we match like everything here with the prefix. Okay, but it's almost the same thing, at least at the start. If we use the information that this is equal to this and look for the corresponding position here. Okay, and that corresponding position here would be exactly I minus L. Okay, because we shift L positions to the left. So instead of matching this with the prefix, we can try and match these with the prefix. Except for one small thing. Basically, so okay, we try and match these. So we know that these are equal, right? These substrings are equal. The thing is, we don't know about the next character. In fact, we know that they are different because otherwise we would continue our that function forward. So our knowledge of matching here only goes as far as R, and here up to R minus L. So what happens here is that yes, if we try and shift this information here, we can only go up to here. So, but still, let's take a look at the value of Z I minus L, and there are a few cases what can happen. So let's look at this particular value of that Z function. So it means that we have a block here that matches with the prefix and also matches with the corresponding substring right here. Okay. So if we assume that this substring ends before the end of our Z block, then since it cannot be continued forward, it cannot be continued forward here, so it cannot be continued forward here, since we still have the correspondence within the substrings. So these are different characters like A and B, and here never mind, something. Oh, we have A and A, but here we have B. Okay, so we can see that these cannot be continued. So in case when we have Z I minus L, let's see, it's probably I plus, so if we try to go from here, so the length, if it is less than R, then we must have that Zi is equal to Zi minus L. Okay. Otherwise, basically, if this string rather than being short goes way too long over here, then we cannot extend our knowledge, because past this point we don't have like any equalities anymore. So in this case, what we have to do is to truncate our like this substring at the position R and start comparing starting from the position R. So if we were to like unite these two cases, then what we are doing basically is we are putting the value of Zi equal to minimum of Zi minus L and also R minus I, like that. And after that we are going to we are going to try and increase our Z block by continuous iteration. So we are going to write while Si plus Zi is equal to Szi. While that holds, we increase Zi. Okay, like if we didn't have this line, it would be just a trivial computation, right, of that I. Basically just comparison character by character. Okay, but if we do this first, we reuse the information that we had from the previous blocks to skip a few iterations if we know that the characters are like guaranteed to be correct. Okay. So it's not a complete code by any means. Let's try and write some complete code. So we will have that, but let's write from scratch so that we'll know what happens. Okay, so first we are going to have L and R equal to 0, and one thing yes, okay, so one thing is I mentioned that before at I don't know exactly why, but we have this range here, and it didn't matter to understand the idea, but for the purposes of the code, we are going to assume that it's a half range. It's a half interval. Okay? It's not going to be too hard. If you are used to using segments, it's okay. But I think it's more universal in most cases. So for example, we can write L equals R equals 0, and that corresponds to an empty set basically. And if you try and think how do you represent the empty set with a segment, you have to do something weird basically. Anyway, let's try to compute our z function here. So first of all, there are cases when there are basically no z blocks that cover our position. For example, if there is a new character, then there is no z block that covers the position. So if that happens, like we still want for our index to be kind of inside the range. So if I is greater than R, we are going to say that L is equal to R is equal to I. Just so we don't do some nonsensical things when I is outside of the range. Okay, so now we go somewhere. We do it like this, basically minimum of Z I minus L R minus I. So you see, the reason why we wrote these lines is that if I is greater than R, then for example this thing is negative, and we kind of don't want that case. Yes, and here we use the Z0, which is, so for the purpose of this particular implementation, it's convenient to set it to 0. Okay, so that kind of makes sense, I think. Yeah, never mind. Now we are doing this cycle here, except that if that I gets too large, we may get outside the string basically. So we have to check that basically this particular index is within the string. So we have to have I plus that I less than n, and also this thing. Yep, which is that I plus equals 1. And it's almost all, except the fact that the only way we can update our z block is here, and we kind of have to make it actually work. We want to update it with something more sensible. So in fact, to update it, it's sufficient to write it here inside the cycle. L equals to I, R equals to I plus that I. Okay? And it may seem that, for example, so okay, if we are matching something, then, for example, let's assume that it could happen inside the string here. So if we are matching here, then like we are continuing forward here, then we're kind of decreasing our right endpoint of the z block. We probably don't want that. right? Because if you remember, the Z block is out of all matches between the prefix and the substring that starts at ith position, which is what the Z function is all about. Then the Z block is we consider everything we have computed by this point and choose the match that has the largest right endpoint. Okay, so the largest I plus that I basically. Okay. So we don't want to decrease that, obviously, if we introduce new values. So why do we do it here? And the reason is we don't, because if our match ended inside the Z block, then the next comparison is guaranteed to be a fail. Because basically, if we could continue it here, then we could continue it here as well, so that the Z function could be increased. So my point is, it works. So basically, this naive comparison happens only when we are past R. Okay, so when we have our chance to increase R, actually. Well, yes. So this is basically the whole code. I don't think it has any problems with that. Are there any questions about, like, what happens? Who is this person inside of me? I don't know. Like here? Hmm? Greater or equal to R? Yes. Well, okay, the only bad thing that could happen is, like, if I is equal to R, then what happens is we are on the border of that block, and since I is equal to R, then we initialize that I to 0, so that forces us to make naive comparisons here. So for safety, like, if you feel safer, you could write I greater or equals to R. It would be correct as well. There's no problem with that. Okay. Yes. So in fact, basically, like, they have an equal amount of information, but they are represented in a different way. And by having equal amount of information, I mean that if you have a prefix function that you can unambiguously construct the Z function, and if you have the Z function, you can go backwards, again, unambiguously. So, well, I guess that answers that. About the correct way to make this transform, I think you should. Well, you will have a chance to think about that. Let's just say that. Any more questions? Please don't hesitate to ask questions. I know it's basically the last day to do that. At least to me, yeah. Hmm? Yeah. Hmm? In a certain way, yes, you do have a tree. Yes, I think so. I'm not able to come up with a particular example, but, well, basically, yes, we are constructing a tree, and then we are moving back, like moving towards the root, and then introducing some new branches. That's one way to look at it. Yep. Okay. So, how much time do I have left? None, I would expect. 9:30. Okay, so at least half an hour. And we didn't prove anything about the Z function yet. Basically, we don't know why, if it works fast or why it works fast. And the reason for that is even simpler than our analysis of the prefix function. The reason for that is that, so okay, which of the lines could work more than in linear time, right? So all of this is constant, basically, and then we have this cycle again, and we don't know how long it takes to do a simple pass here. But the thing is, we kind of understand now, like it is important, so it may be a good point to ask a question. The thing is, in this cycle, R on each iteration of the cycle, R always increases. Okay, because we cannot run this cycle while we are trying to extend within another Z block. Basically, within that Z block we don't extend. So the only chance that we have to run this cycle is when our Z function is like exactly pointing at R. So here we are obtaining minimum at this position. And after that, each particular iteration of this cycle increases R. And that's the reason why, so obviously R cannot be greater than N. So that means that this cycle has in total at most N iterations. Okay? Makes sense? So basically, we had a naive algorithm, right, of computing the Z function. And then we made this optimization that made it to cut off a lot of excess work, and now it works in linear time. Okay. Any questions about everything so far? If not, then we will go to some other ways to... Well, the substring matching problem is mostly done for the purposes of this lecture, at least. The only other useful way to match the substrings is called the polynomial hashes. And looking at the questionnaire, I believe that a lot of people should be familiar with that, at least more than with the prefix function. So please raise your hand if you are familiar with the polynomial hashing. And okay, well, let me just state some things so that what does it do. So basically, if you have a string S, the polynomial hash is usually computed modulo a certain number p with base q. So basically what we do is we represent S as a sequence of numbers, and then we consider it as a polynomial, and then we evaluate it modulo p. So there are a few ways to compute hashes, but the one I find the most convenient is when the last character of the string corresponds to the lowest digits, basically. So we are going like sum from I to from 0 to n minus 1, if this is numbered from 0 to n minus 1. So it's basically q to the ith times s n minus 1 minus I, and that's modulo q. Okay, so it's basically polynomial in q, and characters are coefficients if you represent them in numbers. And now we can see that, for example, hash of the string s plus the character c is exactly q times the hash of s plus the value of c, well, modulo p, obviously. And also, if we know the, like, if you have a string and we know the hashes of like a prefix and the whole string, then we can also compute this one, basically just by multiplying this number, the hash of the prefix, by a certain power of q, and then subtracting from the whole hash. And that is useful because if we know the hashes, like assume that we have a string, right? And we compute the hashes of all prefixes here. And now that we have it, we can compute a hash of any particular substring in constant time, because all we need is the hash of, like, if this is this substring, right? So we only need the hash of these and the hash of these. So in a nutshell, that's how we use hashes. And to match a substring, basically we just compute hashes and then do this. So maybe if you are familiar with hashes, you still have some questions you want answered, like you have some doubts, or you wonder why it works at all, or something. Okay. So the last basic algorithm or data structure or whatever about the strings that we're going to talk about is called the trie. And we've kind of mentioned it yesterday in the analysis of the last problem. So what a trie is, it is basically a convenient way to store a dictionary of words. So assume that we have some words like this, maybe also A, also like this. I don't know, some words. So what we want to do now is we want to construct a tree so that basically the nodes of the tree are, junctions, and from each junctions you have several pointers. Like if you want the first letter to be A, you go here. If you want the first letter to be B, you go here. And if C, you go here. Okay, so after that we arrive at another junction here, and we have the same thing. Like if you want to go to A, you go here, or to B, you go to here. And basically the tree looks something like this. Okay, so naturally we don't want this to be ambiguous at any point. So like if you're just walking around the city, you probably don't want to arrive at the junction and see the pointers to the same thing pointing in the opposite directions. It doesn't exactly make sense. So what that means is that for every node, we want all these arrows to have different letters, right? And by this we have everything unambiguously. So if this is a dictionary, then one thing that we would probably want to do is to check if a particular word is in the dictionary, right? So how do we do that? Well, obviously if we try to go from the root, and like if we want to check the word CB, so we start from C, okay, we go here, and then there is no pointer that corresponds to B. So that already means that there is no word CB here. But there are other ways, there are other situations. For example, if it's just B, then B is not in the dictionary, but we can follow the arrow, and so we cannot quite tell which word is in the dictionary and which is not. So we need some additional information, and for that we will mark certain vertices, certain nodes of the automaton. That's the next lecture. Of the trie as terminal. So that means, okay, this is the end of some word in a dictionary. So in addition to having all of these, we are going to mark this vertex here, 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 and I guess here, and this is not a mark, just a root, and here and here. Okay, so now we are good, because if we have B, we go here and say basically, okay, there is a way to get here, but it's not the end of the word. So not in the dictionary, sorry. This is a way to check if a word is in a try, assuming that the try was already constructed, right? And to construct a try, it basically you do the same thing. So if we want to add a word, for example, I don't know, CAB, okay? So what we are going to do is we are going to follow down our directions, except if we have no corresponding direction, then we have to make one. Okay? So first we try to go with C, and okay, from the root we can go with G, right? So we go with G. Now we're here, and we want to go with A, but there's no A. So we introduce A. We also introduce B here. And for the very last vertex that we create, we mark it as visited, basically. Okay, so this is how we create a try. It's a convenient way because you can see that the amount of memory it takes to store all the words is almost the sum of the length of the words, because we have to go into a bit of implementation here to understand the almost part, but it's a tree and its size is roughly the total size of the words. And basically all the operations take linear time, right? Because if you have a word of length 10 and you want to do anything with it, basically check if it's in the dictionary or edit, it takes exactly 10 steps anytime. So let's now let's discuss the implementation a little bit. It's not too hard, but there are a few things to consider. Usually, it is recommended, like I recommended to you. So you have a nodes here, right? And you usually number them with numbers. So to each node we put in association some information, which is basically the arrows, right? And also if it's terminal, and also in some problems you may want to store some additional information as well. Okay. So since you have to store a lot of information together, one way you could do that is you could create a lot of arrays that have and just use the same index over and over. But a good way to do that is to put everything in a structure. Okay, so what are we going to have in a structure? Like what are we going to have to describe a node, right? The first thing we are going to have are the arrows. And the thing with arrows is we don't exactly know how many arrows there will be. Like, well, certainly we know that if we only have like 26 letters, then there can be at most 26 arrows. So if your alphabet is small, like there are only letters, a good way to go is to create just a static array inside the node structure. And you may probably want to define the default constructor to set it to some certain values if you want. So here the value of each of these is either the number of the corresponding node if there is a way to go there, or if there is no error we might want to indicate it, for example, with -1. Okay, so these are arrows, and we also have if vertex is terminal, and that's basically it for now, at least. So now we create an array of these structures, And you may go with an array. You may want to go with the vector. I don't know. I usually call it T because I'm good at naming. So you may want to use a vector because you don't know in advance how much nodes would you use, and so it's a bit of more economical to use a vector. But you may as well go with a very large static array of these. Okay. And now we could write the functions to actually, look for a string in a trie, or add the string to a trie. Does anyone want me to write the code? I think it's pretty much self-explanatory how you should go about it. But if you want to, please don't hesitate to ask it. Completely okay. All right. So, do I have any time left, perchance? 15 minutes. Oh, okay. Let's see here. So let's solve another problem. Basically, using trie. So what do we have is we have a string of length, like let's say it's at most 2000, and then we have to process a lot of queries that are templates. So this is basically a text. These are templates, and the total length of the templates can be up to 1 million. Okay. And we want, for each of the templates, we want to find the number of occurrences of this template in the text. Okay, so it's a kind of a substring matching problem, except we have to process many queries. And so if what we could try to do is we could apply our algorithm to each pair of So independently, we are using, for example, the KMP. We're finding these in these, then these in this, and so on, right? The problem is, if we do that, then, like you remember, we construct the string like this, okay? So the total complexity would be the total size of all these strings. So that would be like the sum of cheese would be 10 to the 6th, that's okay. But if all the strings are short, it could happen that the sum of these would be 2000 times 1 million. And that's a bit too large for us. So we want something that processes each string. Like you can see that we almost want a linear time, but we may use the fact that the string is very, it's not too large, and we may want to preprocess something because it never changes. So, any ideas how we do that? So, okay, we know that if we have a dictionary, for example, then we can use a trie to search words there very fast. Okay? Can we reduce our problem to like the dictionary one? Yes. Yes, exactly. So we are going to solve it with trie. And what we're going to do is to take all suffixes of our string and add them as the words of our dictionary. Okay? So for example, I don't know, if the string was A, B, A, C, A, then we are going to add A, B, A, C, A. and okay, this is terminal, BA, CA, and then ACA, and this is a terminal, so then CA, this is terminal, and then this is terminal. Okay, so we obtain some trie that contains a lot of suffixes, and now we want to check if something is a substring here. Okay, well, we want to count them, but let's consider the case where we only want if it's a substring. So if it is a substring, that it must be a prefix of a certain suffix by definition, basically. So if it's a prefix, then if we follow our way, like if we follow through the trie using some string, then it must never be the case that there is no pointer that we can follow. Okay? And vice versa, if we have followed our string and everything worked for us, then it must have been because of there is some suffix that with prefix like this. Okay, because we have created this path for some reason. So yeah, what we are doing is we are constructing this trie, which has the size of n squared. Well, as a matter of fact, it's n squared times the size of the alphabet, but never mind that. And then basically doing everything here is just the total size without any logarithm or something. Okay, but now let's assume that we want to count the number of occurrences, okay, of each string. Should it change too much of our solution? Okay, so how do we do that? Yeah, good point. So basically, when you are adding a string, okay, actually what you want to count is, well, one way to do that. So basically, if you have A, right, then you are in this position, and each occurrence of A corresponds to a suffix that can be reached somewhere down from this vertex. Okay? Or maybe the same vertex. So basically, if you look at this terminal vertex here, the ACA, it corresponds to the occurrence here, because we can go all the way to the end and read out all the rest letters. Okay, so the number of, like, again, almost by definition, the number of occurrences of a string is the number of suffixes that start with the string. Okay, so, and if a suffix starts with the string, then it must be somewhere in the subtree of this node. Right, so basically for each node we want to count how many terminal vertices are there, like, in its subtree, basically. So what we are doing is, well, it's pretty simple to do, because when we are adding our, so we will need another field here, but that's all, basically all. So if we are adding some string, basically while we are adding it, we are going through some nodes, and we know that in each node that we visit, we have to increase this counter by 1, because these are exactly the nodes where we want to do that. So here we have +1, +1, +1, +1, and also in the root, for some reason, +1. Okay, so there is actually a way to solve this problem for much faster, for a much larger string, like if this is up to 10 to the 6th as well, which is kind of going to be in the second lecture. There are several ways to do that with something called suffix structures. Basically, one way to do that is, if you look very closely at this tree, you can note that it has at most n leaves, right? Because every leaf corresponds to a suffix. And so there must be at most n leaves. But if you have a tree without any internal vertices of degree 1, so that basically if you try and contract all these long chains of vertices here, then what you obtain should be a tree with at most n vertices. So there is a hope to use this kind of thing for the longest strings, and there is actually a way to construct this compressed tree in linear time. It's kind of complicated, but yeah, okay. The last problem that is like a good indication of how useful everything of that was is basically if you have a string of length n, you want to count the number of distinct substrings of that string, okay? And you want to do it in time n squared. There are, again, a few ways to do that. The way 0, because it doesn't work, is we may compute the hashes for all for all substrings and then count the number of distinct hashes, right? If you use, like, it depends on how do you actually count the hashes. If you, I know you can't sort them because it takes n squared log time. You can't make a map out of them because it takes n squared log n time, but you can make a hash table out of them. So it's kind of, I don't know, I don't like this a whole lot, basically. So a lot of hashing, okay? Just to know, how many people here know about unordered map in C++? Yeah, so basically instead of map you can write unordered map. And sometimes it works faster, but it needs but you need to, sometimes you need to define the special structure that counts the hash of your object. So okay, can we find another solution with basically anything that we've discussed today? Yeah. Yes, exactly. If we construct the suffix trie, right, then the number of nodes there is exactly the number of distinct substrings, right? Because every substring will. Okay, so let's look here. If you look at A, right, it occurs 3 times, but we have only a single node here. So basically, a node exists if and only if at least one substring exists with the corresponding path. Okay, so we claim that the number of distinct substrings in a string is equal to the number of nodes in the suffix trie, and we can go on and like write all of them down. So okay, the root corresponds to an empty string. Sometimes people write epsilon for that. Then we have this node, it's A. Then we have that node, it's B, ABA, ABAC, and so on. Okay, so you can see that a string is present here if and only if it's a substring. So this is a solution in, yes, basically in n squared time, assuming that the alphabet is small, which is usually the case. Oh, I didn't mention what you should do if the alphabet is large. If the alphabet is large, for example, you want to store sequences of numbers up to 1 billion, then instead of these, you use a map. So basically, you create links as you go, and that introduces another logarithmic factor into the solution, but at least you don't have to create very large arrays. So yes, here it is the number of nodes in suffix try. There are some other more clever ways to do that. Well, I guess kind of more clever. Maybe it's just complicated for no reason. We can compute the number of distinct substrings actually with let's compute it with the prefix function. Is it clear how to compute with the prefix function? Probably not. But the thing is, let's consider a string and let's consider the last character. Okay? So the last character, so let's see, after adding the last character, how many new substrings do we obtain? Okay? So basically what happens is that, okay, so that letter might have been already somewhere. The last two letters also might have been somewhere. And up to some point, a substring will not be new, but after that, all substrings will be new, like this one. Okay? So there is a point, basically, where old substrings are, well, they finish and only new substrings are present. So if we add this to our string, the number of substrings we have to add to the answer is exactly the length of this part. Okay? So how do we find it? How do we find the largest substring that ended here and occurred before? And if you think about it, like if this occurs over there somewhere, if we flip the picture, right, this will be exactly a prefix suffix match at a certain position, right? So this will be indicated by the prefix function in some position. So to find this, we reverse our string, compute the prefix function, and find its largest value, basically. And that corresponds to the largest string that occurs somewhere else, basically. And it takes n² time. And it's not too hard. We can just reuse the prefix function, basically. You can also go with the z function, but you can think about it for yourself. I think I'm way out of time, right? It's like, huh? Oh, cool. Okay, so that's it. And after a short break, we're going to talk about some hard stuff. Okay. Okay. If you're waiting outside, please come in. We're going to start now. I hope everyone's back. Guys. 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 Please sit down. We're going to start. Okay. Is it on? All right. So this is going to be about some hardware algorithms on string, and like how do you solve tasks with strings. And the main focus will be on something called suffix structures, which allows you to solve a lot of problems in the best time possible in linear time, like substring matching and dynamic substring matching. So the suffix structures are a very cool thing that allows you to solve a lot of problems very fast. It's almost it's really fascinating how powerful they are. There are a lot of them. We're going to discuss one of them because really it's the most useful and also allows you to basically use every other structure as well. But before that, I thought we could cover one extra algorithm which is not concerned with suffix structures, and that is something called Tikhomirov algorithm. So, but before that, I want to know if actually this is needed. So please raise your hand if you did not attend the basic lecture, but you don't know what Tikhomirov algorithm is about. How does it work? Is that too hard? Too hard of a question? Okay, let me write it down for you. So you didn't attend first part, and okay, and don't know the Tikhomirov. Maybe that's a C. I don't know. So, if you satisfy this query, please raise your hand. I'm only interested in the number. So apparently everyone does, and that means we have more time for covering. Okay, and if I drop this condition, okay, a fair amount. The thing is, this is still an important algorithm. It's it's kind of concerned with matching multiple templates in a text at the same time. So it's basically you construct a try on the templates, and then you do some stuff on that, construct some additional information, and the main basically what you do is construct. So if you have a lot of templates and you want to match all of them in a text, what you do is you construct a try on all the templates that you want to look for, and then you process the text letter by letter. And actually this try has like all the information we need about matching the templates. So yeah, we also have the terminal vertices, right, that correspond to the actual templates. So what we want to do here is that if we process a text at any point, we want to maintain a vertex in the trie that corresponds to the largest suffix of the text that actually occurs here. Okay. So basically, to do that, we want to, like, if we are in a particular vertex and we append the letter that we can go through, then we go through it. And if it's a terminal vertex, then we have found something. But it could also be that, like, if this vertex is, you can see that in this case, if the largest suffix is here, then we have this template occurring ABB, but also B, right? So we want to kind of know that. So the thing we are going to construct in this trie, and this is basically almost the whole reason I'm mentioning that. The thing is called suffix link. Okay, so the suffix link is a pointer from any particular vertex of our trie of templates that maps this string to another string that is a suffix of this one, and this is the longest suffix that occurs there. Okay, so this is the next longest suffix that the next longest suffix of this string that occurs in the trie as well. Okay, so this is an important concept, the suffix link, and it's going to occur further, like in the suffix automaton that we're going to talk about. So if you were able to construct this, then the algorithm to move our pointer is to basically, so if we're at the vertex V, while there is no arrow with C from the current vertex V, where C is the character that we're appending. So it's not B, it's C. So while we do this, then we go from V to the suffix link of V. And after that, we go from V to, like, to U that occurs by traveling along the character C. And after that, we have to, if we have to find all the templates, they kind of end here, then if we are at the vertex V, then all these templates are, we can obtain them by starting at the vertex V and traveling upwards by suffix links and writing down all the terminal vertices that we reach. Okay, that's the general idea of that. So it's like trie on steroids, basically. You introduce a lot of information and you use it. So yeah, a good description. Yeah. So you have to make it. So computing the suffix link is not that trivial, but you can do it with a kind of BFS, like you are doing the dynamic programming on that, like from top to bottom, and use previous suffix links to obtain the next suffix links. And you also have to be careful how you actually obtain the templates that end here, so that it doesn't take too much time to travel all the suffix links that do not lead you to non-terminal vertices because you don't want them. So with suffix links, you want to compute something called strong suffix links. That is the closest terminal vertex reachable by suffix links. Okay, so that's the general idea. And if if some of you are still interested in that algorithm, you can either read that up or I can explain it to you like sometime later. Maybe if we have some time left in the... Oh, we don't have a discussion today. We have a pizza, which is not too bad. So yeah, anyway, if you're interested, I may be able to find some reference for you or just explain it, how it works. So we'll figure that. So the suffix link is going to be important. Okay. So now let's talk about suffix structures. And the most important suffix structure to understand, like not to actually use, but it's a really good like mental model on how do you work with substrings of a particular string. Okay, and this structure is called suffix tree. So at the end of the previous part of the lecture, we've discussed a solution to a certain problem, which basically involved taking a string S, right? So we take the string S and produce a trie that consists of all suffixes of S, right? That's exactly what we did, basically. So I may just as well write it down again, right? So A, B, A, C, A, then we have B, A, C, A. So we are adding suffixes basically in any order. So we are doing this, and then we are doing like this, and we are doing CA, and then we are doing A. So these are terminals because they correspond to the suffixes. And also the root is also a terminal because there is an empty suffix. It's just convenient to have it there. So the suffix tree is cool because, for example, you can search for substrings in a certain string. So if you are given a string and you want to check, you are given a template and you want to check if it's actually substring. So if it's BA, the only thing that you have to do is to start from the root and follow down the arrows with the corresponding letters and check if you can actually do that. And if you can actually do that, then it must mean that it's a substring because it's a prefix of a certain suffix. Okay, so that's how it works. That's one application, probably like the most straightforward, right? Some other applications, like basically stem from the fact that it's a tree and we can do things with trees, right? For example, suppose that we have two positions in our string. So for example, here and here, and we want to find basically something resembling the z function. So basically we want to start at these positions and see what's the largest length, so that if we start from here and start comparing, we obtain equal strings. Okay, so here if you start from this position and this, then we can have only one comparison that matches. Okay, so this problem is called LCP, which stands for longest common prefix, and that is because we are considering basically two suffixes of the string and we are looking for their longest common prefix. Okay, makes sense? So great. So how do we approach this problem if we have a suffix tree? So we want to suppose that we have a lot of queries and we want to do that fast, and the string doesn't change. Yes, exactly. So since this is a tree, then we consider these two suffixes. We consider the paths to them from the root, and then the longest common prefix is exactly the common part, right, of this path. So if we like translate this to the tree language, we see that this vertex is exactly the LCA. Okay, so LCP is LCA in suffix trees. Which is cool because we kind of know how to find LCA in logarithmic time, or you may even know how to do it in constant time. So basically, if you have a suffix tree, then you have a useful model that allows you to interpret questions about substrings in terms of something happening inside the tree. Okay, so another, like, the application why we've discussed the tree was to count the number of distinct substrings, and obviously in terms of tree that corresponds to the number of vertices here. Okay. So yeah, the moral is, if it's a problem about substrings, then probably it is some problem that concerned with trees in terms of something happening inside the tree. Another application of that, like, just to give you perspective, is you may have encountered the problem. You have a string S and you have a string T, and you want to find their largest common substring. Okay? So we want to find the substring that occurs both here and also here, somewhere. We don't care. Okay, so how can we solve? There are a lot of ways to solve this problem, but how can we solve it if we have a suffix tree? Again, we want to reinterpret that in terms of something happening inside the tree, right? So, yes, basically it's the lowest node that happens in both trees. Of, like, if you construct the suffix tree of S and we construct the suffix tree of T, one way we can think about is we intersect these trees, right? So we may go down a letter if and only if it occurs in both of the trees. So we obtain some kind of intersection, and that consists exactly of all common substrings. Okay? And since we want the longest one, we are looking for the lowest node in this tree. So another solution that involves only a single suffix tree is that from these strings we may construct a string that goes something like this, basically. Okay? And so it's S, then it's some character, some ugly character that does not that is not contained in any of these strings. So it's a new character, and then this is another new character. Okay, so these are markers to help us see that's okay. That's the end of one string, and that's the end of another string. Okay, so let's build the suffix tree for this one. And if we build a suffix tree for this string, let's try and understand what, like, how can we find common substrings in this tree. Okay, so we have a string. It's a path here in our trie. If it's like a valid substring, then this should not contain any ugly characters of this kind. Okay? So, and now we want to check if it's a common substring. Is there a way to characterize this? Yeah. almost it's almost true, because if this is a subtree of S, for example, then we will have a path down there, so that first it's the first ugly character and then the other. Okay, so it's almost correct, except for the fact, like, if one ugly character occurs after the other, then the second we just ignore, basically. So we want, so a string is a common substring if there is a way to travel down somewhere and without visiting any ugly characters, and then find the first ugly character just as a transition, okay, from this particular vertex. And then there is some other way to go somewhere else and then encounter the other ugly character, okay? So basically this corresponds to a way to, you know, start from the substring and continue until the end of S and then go past the end of S. And here it is the same, except for we want to go through the rest of T and then go past the end of T. And so here, everywhere in here and here and here, no ugly characters. So this is how we can characterize our vertex in terms of something happening inside the tree, and also some special characters that we use to mark things. Okay? Is it clear how this works? All right. So, okay, now we have reduced the problem to basically the tree one, and now, like, how do we solve such problems in trees? What are the approaches? Well, basically, we can go with, you can think of it as a DFS, you can think of it as a dynamic programming. So basically, for each vertex, we want to determine, can we reach this ugly character and this ugly character? So we want to know two things, right? So for example, we can write a DFS that returns a pair of integers for a particular vertex. So how does that work? We study all possible errors that go down, like from V to A. And so for this particular error, if this is a character C, then, okay, if this is a character C, if this character C is ugly, so for example, if it's, I don't know, the first ugly character, then we have to make it known in our vertex that there is a way to reach this character. But we, if there are some characters past it, then we have to ignore them for the purpose of our vertex V, like here. So we do something. If we have a variable for the result here, then we want to mark that, okay, this character is reachable, and then we may want to call DFS for the child, just for the purpose of. We may actually not even do that, because if you are past this character, then we are bound to be somewhere in this part of the string, and there is no chance to find a common substring there, basically. Okay, because we are only considering the substrings that do not contain any ugly characters. So if this happens, like, then we had that the first part of the result is true. Else, like if C is equal to the other ugly character, then we have the other part of the result is true. Okay, or else if it's an okay character, then we have that the result. Then we must take the result. We also must take the result of our child and do something like this, basically. Okay, so we take the pair and then we. So if the first ugly character is reachable from U, then it must be reachable from our vertex as well. and for the second as well. So this is in fact 2 instructions for first and the second. I just written it in a short way. So and now you want to find the lowest vertex so that it has true and true. Okay. So again, this is a DFS, but you may think of it as a dynamic programming, because what we are doing is we are basically reusing information from our children to obtain the answer for our vertex. So anyway, this is another example of how a problem that's concerned with strings becomes a tree problem that's usually tractable to solve. Okay. So the only thing that kind of discourages us is that the suffix tree here, if you construct it on a string of length n, it can have up to n squared nodes, well, roughly n squared nodes, because that's the sum of length of all the suffixes. And this is a problem to use for large strings, but there is still hope we can use the tree, because if you look at the tree, and so actually most of it are vertices that have only one error coming out of them. Okay, so it seems kind of inefficient, because basically instead of this chain of 4 errors and like 3 extra nodes, we may want to replace it with a single arrow that has all these letters written on this arrow, because there are no branches on the way. Okay, so on this letter we will write like BACA. And if we do this for all edges, like this is going to be CA, this is going to be ACA, so this is a single arrow now, and this is going to be CA. Okay. So what we have obtained now, I think this is compressed as well, right? So BACA. So what we have obtained now is usually called a compressed suffix tree, or in fact the suffix tree. Usually when someone says suffix tree, they want to talk about the compressed one, because it's most useful. So if we think about that tree, then it has at most n leaves, right? Because all the leaves correspond to different suffixes of the string. And another thing, that except for possibly the root, no internal vertices, so that vertices that are not leaves, have outgoing degree at least 2. So in trees like these, the number of internal vertices does not exceed the number of leaves. It's not very hard to prove. So in theory, if we were able to construct this tree, then it would have only a linear amount of nodes. Okay, and it doesn't make it a lot harder to solve some problems with it, because basically you are still able to search for things inside. Like you're still able to search for substrings. You are still able to apply most of the algorithms we've discussed, like LCA. You locate where the suffixes are, and then you locate the LCA. So this is a much more concise form of the suffix tree, and it can be used for a lot larger strings. There are a few questions though. The first question is, well, there is still a problem to use this with respect to larger strings, because we didn't exactly save memory yet. So we've eradicated a number of nodes, but we still have these strings there. Okay, So what are we going to do with strings? Like, are we going to have an arrow and then just have a string tied to it? Like, what should we do? In fact, when we are doing this in a suffix tree, each string that we have on a particular arrow occurs somewhere in the original string, okay, as a substring. So instead of storing the actual string, we are going to store the positions of like where the string occurs. And for all intents and purposes, this is still like a good representation, because, for example, we are still able to search for substrings using this tree, right? We are just going to go from up to down, and now it may take several iterations to go from the start of an arrow to another. And when we are going down, we are basically matching a part of the template with this part of the string. Okay, so it's not too much worse. And if we do that to all strings, then now every particular arrow has only a constant amount of information. So this is now truly a tree of linear size. And the second question is, obviously, if it is such a good structure, how do I construct it for larger strings so that I can solve some problems, actually? The answer is, well, you can, but you probably don't want to do that explicitly. I mean, I may be like adding some, additional scare to the construction of the suffix tree. There is something called, for example, Ukanen's algorithm. That constructs the suffix tree in linear time. And in fact, this algorithm satisfies, it's actually even cooler than that, because Ukanen's algorithm can construct the suffix tree basically on the go. So you don't even have to know the whole string from the start. It basically, what it does is, at each point of time, it has a tree for the current string, and then you say, okay, now I know the next character. And then the algorithm says, okay, I will just make some small modifications to the tree, and here you go, the suffix tree for the new string. So this unlined property of the algorithm is pretty cool. And I believe there are ways to implement it like in less than 200 strings, 200 lines. I think there are some really concise implementations, but I'm not really familiar with how to do that. So we will discuss another algorithm, another suffix structure, but you never want to forget about suffix tree, because we will see it everywhere. If you're thinking about a problem on strings, the first thing you want to think is, okay, what does it mean in terms of the suffix tree? So it should always be in your head, like when you're solving the problem. But more often than not, you will not actually implement the suffix tree. So the other structure that we are going to talk about is called, well, there are a few names for that. It's called suffix automaton. And also, it has a cool name, an abbreviation like this. Your dog. And what that means is directed acyclic word graph. If you like this, you may use it instead. But I'm more used to suffix automaton, so I'm going to use suffix automaton. So the idea behind the suffix automaton is that if you look at the suffix tree, we may try to compress it even further, because, well, let me return the strings here for a time moment. So basically, assume that we are matching some substring. So for example, we could match like A, B, C, A, right? So we go A, then we go B, then we go A, then we go C here, and then we are in position. So if you've only read the 4 characters, then the only continuation of that allows us to arrive at the suffix is just a single letter A. Okay? And if we, for example, match the string, I don't know, CA, then we match the C, and after that, again, there's only a single continuation that can lead us to a suffix, and it's A. Okay? So we could argue that these positions, if we are only going to use the tree for the purpose of substring matching, then these positions are actually quite the same, right? Because, well, basically, if we are in one of these positions, it doesn't matter in which one. So one thing that we can do is, if we wanted to, if we wanted to contract something here, one thing that we can do is we could say, okay, this is going to be a single position now. So C leads here, and this C leads here, and then A goes here. So for the purpose of substring matching, nothing changed. You can still match both A, B, C, A, and also C, A. But now we have one fewer state. Or actually, the number is the same because it was 2 leaves and now it's a leaf, but and this vertex. But you get the point. So we can continue doing that. Like, we can keep looking at positions that are equivalent in terms of what kind of continuations can be traversed from this position. Okay, and this is the motivation for the suffix automaton. So let's try and formalize this. So let's consider a certain position in a suffix tree. So every position in a suffix tree corresponds to a substring. Okay, so there could be V, and this could be a substring of S. So what we're thinking of when we are talking about this, equivalency between different states, what we're thinking of is what is the set of possible continuations, right? So that we are still inside the suffix tree. And we will denote this as the thing that's called the right context. So this is right context. So the right context is like, what can we add to the right so that we arrive at the suffix? Okay, and that's exactly what we mean by how can we continue the string. So, for example, in this string, if we look for RC of, I don't know, the string A, right? So it's a set, and the set continues of first the empty string, okay? Because empty string matters; it's going to matter a lot. And the empty string we will mark with epsilon. So yes, then the next is CA. That's correct. And also BA, CA. So in fact, if you were matching for substrings, then C would also be a correct continuation. But the information for C is contained in C. So we are only writing all ways to obtain a suffix. Okay? So another way of thinking of that, like a suffix tree is cool, but sometimes we have to look back to the actual string. So if you look back to the actual string, then the right context is we find all occurrences of our string, so of our v, and then we write down what happens until the very end. So all these suffixes here. So the right context consists of several suffixes of the original string. Okay? So now we want to formalize our notion, like our idea, of the fact that we can actually to some substrings we can put into correspondent the same state, right? So we will say that two substrings, two strings v and u, are equivalent. So we will write that v is equivalent to u, and that means that they have the same right context. Okay, so for example, as we've discussed before, we have that with respect to that string. For example, ABA is equivalent, ABAC is equivalent to just C, because for both of them, the right context, so right context for ABAC and also for C, consists of a single string A. Okay? Makes sense? So now we want to obtain basically the smallest possible finite automaton, right? I'm going to explain what that means in a minute. Basically, we are going to obtain a graph that's like, so the way we use the suffix tree for string matching, we can use basically any graph. It doesn't have to be a tree, right? So it can have like these parts which do not occur in the tree. So we want to obtain a graph like this, and we want to obtain the smallest possible graph, so that it has as few states as possible. So let's try and do that for, I don't know, for this particular string. And the way we do that is, if you think about it, so okay, we can compress the, so we can say that two different substrings correspond to the same state without our automaton, within our graph. Okay? But if they have different right contexts, that we cannot correspond them to the same state, because if for each state there is a set amount of continuations that you can follow, basically. Okay, so for example, in no graph that can match substrings of ABACA, we can have, like, we can start from somewhere and then follow a string, I don't know, A, and also follow the string C, so that we arrive at the same state. Like, it could be in theory, but it wouldn't be correct, because after A we can go with B, and after C we cannot go with B, for example. So A and C in fact have to be, so from the initial state, A and C should be different letters. They should point to different places. And also B should be pointing to a different place. Okay? Because for all of these, their right contexts, which we're looking at, are different. So all of these have to be different states. Okay, so what is the way that we can continue our A? So it's either B or C. Okay? And also it's a terminal vertex because it corresponds to a suffix. We like mark this terminal vertices. So we have this B and we have this C. But if you think about it, then these two vertices have the same right context. Okay? So the right context of B is equal to ACA. And also this is the right context of ABA, of AB. Okay. So it will not hurt it if we take these two states and glue them together. Okay, because their continuations are going to be the same anyway, just like we did here. It is still going to be okay. So instead of introducing a new vertex, we may draw an edge here and say that B just goes here. Okay, so we save something, and we can see that the same thing works with C here. So C can go here. Okay, now what happens next? Basically, we can continue ABA. We can continue either C or AC. It doesn't matter. With the letter A, and that corresponds to the so-called okay, I don't know what to call it, but the right context for that is only the empty string. Okay, so here is only the empty string. Now here we can go with A, and we will obtain right context CA, which never occurred before. We can also go with C, and then after we go with A, we arrive at the same last vertex. So if we were to mark the terminals, it would be these, and I don't know why I marked that. So it's A. It's also like ACA should be terminal, so ACA. So this is terminal, BACA. So there are only two terminals here. So this is in fact the most concise graph that only accepts the substrings of our given string. Because we know that there are at least as many states in our graph as there are different right contexts for different substrings. Okay? So this is the best we can do. As you can see, this is very concise, but it is concise in a lot different sense as, like, for example, the suffix tree is concise. Because suffix tree is concise because we've compressed this path here. And the automaton is concise because we reuse a lot of states. But actually each transition is only one letter. Okay? It is not quite clear how large the suffix automaton can be, and it's not easy to prove either, and I don't think I will go for that. But it can be shown that the suffix automaton for any string has the linear number of states and also the linear number of edges, right? So, and it even holds for like larger alphabets. So the tree will estimate, like, if we were to have 10 to the 9th different letters and vertices, then for example all of them have outcoming degree 10 to the 9th, and then we would have much larger number of edges. But we can bound the number of edges just by, I want to say 3n. So the number of vertices is at most 2n, and the number of edges is, I think, at most 3n. So yes, this is going to be concise, but again we are going to ask the question, how do we actually construct this? And even if we construct this, can we solve any actual problems with that? Because this seems optimized in terms of the size, but can we actually solve problems in terms of that? The answer is suffix automaton is, in practice, it's even more useful than the suffix tree for a few reasons. The first reason is you can actually recover the suffix tree from the suffix automaton, like if you look close enough in linear time. I will talk about that after we've discussed the algorithm, perhaps. The other reason is that suffix automaton has, in fact, some extra information, and some problems are better solved with suffix algorithm rather than with the suffix tree. I'm not sure if I will be discussing these problems like right now in lecture, but there are some in the contest, or at least there will be. So okay, we want to construct our suffix automaton, hopefully in linear time. And once again, our algorithm that we're going to discuss is going to be online. In terms of after adding every character, we are going to have a valid suffix automaton for the constructed part. Okay. So the first, like before we have any letters, we have the empty string. So at least we have one state that corresponds to the empty string. We may as well construct this automaton by adding letter by letter. Okay, so if we add the letter A, then it goes something like this. So the right context here is only A, and the right context here is only empty string. Okay, now we do add B. So let's try and think about what happens when we add a letter. And by what happens, I mean what happens to the right context of these different states. Okay, so if there was a state, and we were able, so if there was a string, and we were able to basically to add some suffixes to it to get to the end of the string. If we add a new letter, like for example we add the letter C, then what happens to the right context is all of the strings in the right context just get prolonged by C. Okay, so after we add the B here, then since we were able to get to the end by using A, then we are able to get to the end by using AB. And here we are able to get to the end by using just B. But that's not exactly all that happens to the right context, because it could happen that this particular string here is now also a suffix. So it's present here. Okay? So for every state, what happens to the suffix, to the right context, is that all of the elements get prolonged by the new letter, and also epsilon may be in the right context as well. Just for this letter. It was not there before, but it's going to be there now. Okay? So yes, so here is what happens, and we can see that nothing much happens as well, at least, except we should create the new vertex that corresponds to the trivial right context, which is just the empty string. Okay, so this always happens. We always create a new state that corresponds to the trivial right context. Okay, because we have a new string, which is namely the whole string that is only present, so that its right context is only epsilon. And we can't have among the previous ones because, you know, they have something except for the epsilon, like non-empty strings. Okay, so now here we have B here, and what? I mean, yeah, no, I think that's good. Okay. Or is it? Okay, I know what I did wrong. The thing that I did wrong is that I was assuming that at the previous stage, the right context of this vertex was A, but it's in fact A and epsilon. So now, as we get B, it becomes AB times B. So now we can see that. So now we can check also. So yeah, there are like three 3 different substrings. Okay, there are 4 different substrings, but 2 of them are equivalent, so they're here. Epsilon is still here. That is a good point, yeah. So this is an example of when sometimes epsilon gets into the right context just by itself. Okay. So yes, and that goes on. The fact is, we didn't see everything yet that happens to the suffix automaton, because let's talk about the strings that lie in the same state. Okay, so the strings that are equivalent. If you look at 2 strings that are equivalent, then okay, 2 strings are equivalent, so there is a set amount of positions where they can occur in the string. Okay, so for example, one string, all of its occurrences end at positions 2, 4, and 6, and for the other it's again 2, 4, and 6. So that means that they are equivalent, right? And if we look at that, so it goes like this. Okay, and we can see that if 2 strings are equivalent, then one of them is necessarily a suffix of the other, because of this picture. Okay, so if 2 strings end at the same position, then one is the suffix of the other. So yes, and also we can see it is not too hard to see that if we have 2 suffixes and they're equivalent, then all suffixes between them are also equivalent, because basically they cannot have more occurrences than the smaller string, but they also cannot have fewer occurrences than the larger string. So in fact, we can like describe what each equivalence class looks like, and each equivalence class looks like a substring, and all the strings that are equivalent to it are its suffixes up to a certain point. Okay, so what we are doing is that we are taking a string and then start erasing the first letters until it just so happens that the right context changes. So yeah, for example, if we have the string I don't know, like CABC ABC. Okay, so and we look at the right context of ABC. So the right context of ABC is ABC and epsilon. Okay, then the right context of if you erase the first letter. Okay, so we erase the first letter, so it's BC, and then it's again the same thing. But if you now erase the B, then we get then our right context changes, because the new string is small enough to occur somewhere else, basically. So what happens is our C of C is now ABC ABC, and also ABC, and also epsilon. But the thing that we can notice is that when we erase the first letter, the right context, the only way it can change is that it can expand. Like some new strings could get in there. Okay, because all the other occurrences are still there, and there could be just some new ones. Okay. So the useful information that we're going to have is basically for each state. Okay, so we know how to describe all the substrings in a state. It's a substring, and then like all strings up to a point. So after that point here, what happens is we go to a different state, right? So we go to a different state, and then we have this situation as well, until we go to a further state, and so on, until our string is empty and we just arrive at the starting point. Okay? So the information we are going to use is basically the transition from here to here. Okay? So the transition is we were in this state, and we want to go to the next state that occurs basically at the first point when something changes, when we erase the letters. Okay, so for example, if we see it here, then so here the right context is. So yeah, let's just look at which strings lie in each state. So here we have the strings A, B, and also B. So that means that we have A, B, and we can erase the letters up to this point, right? So here we only have, I think, we only have A. Okay, so we only have A. And that means that after erasing the first letter here, we go to a different state. And then we have this, which is only an empty set, an empty string. Okay, so epsilon, and it doesn't make sense. Like you can't erase any letters from epsilon, so we cannot define the transition here. So we can see that. Something's wrong, probably. Like, yes, I was wrong here. If you erase A, then you go from A, B to B, and that leaves us in the same state. Okay, so we can erase letters up to here. So only when we get to the an empty string, then something changes. So we have our pointers from both of the states going to the empty string, and these things are called suffix links, just as in Achokoresak's algorithm. So the reason why, like, if something is called suffix links, it's usually because you erase something from the beginning, so that it points to some suffix of your current state, which is different from where you are right now. Okay, so this is why it's called suffix links. So we can see, for example, that suffix links form a tree in the suffix automaton, because basically, like, okay, obviously it cannot have any cycles, because if we travel through suffix links, then the length always decreases. So it cannot have any cycles, and also if we start at any vertex and then travel far enough, then we arrive at the root of our automaton. So it is a tree. Okay. Can we actually use that to obtain some useful information about automaton? For example, one thing that we can notice is that the terminal vertices are like, so we have two special vertices in our automaton. First is the start, right? That corresponds to the empty string, and then like the ultimate terminal state. It's here, so that the right context is only the epsilon. Okay. So this vertex still has like a suffix link, so we can start following them, and in fact the terminal vertices are exactly the vertices that basically that are reachable by suffix links from our finished state. Okay, because because if it contains epsilon, then it must be, so a terminal state is the one so that its right context contains epsilon, so that it's a suffix. And if it's a suffix, then it's a suffix of the string that lies here, so we get there after erasing enough letters. So all the terminal states in our suffix automaton form a chain in our tree, form a path. Okay, so now let's get back to actually changing our automaton, so that when we had a correct automaton, we want to have a correct automaton in the end. So what do we know by now is that the right context of any string changes in a predictable way. So all strings expand by the letter we have just added, and also probably the epsilon can get into the context. The thing is, sometimes it could happen that let me think how that goes. So we have like E and E, right? So we have strings A, B, and B here after 2 letters. Let's try and, well, we're not going to rebuild the whole automaton, but we are going to try and add letter B and see what happens. What happens? So basically, okay, we have like A, B, and B here. Right, context is epsilon. So in the new string, like we have A, B, B now, and it didn't work. The thing is, sometimes the strings which are in the same state. Well, okay, so there are several suffixes here, okay, and sometimes, basically, the strings that were equivalent, a part of them receives the epsilon, and the part of them does not receive the epsilon. And in this case, we must make them non-equivalent anymore. But that will probably occur later anyway. Well, let's try and figure out. What happens to the strings, right? So what we want to do is to, okay, we have some right contexts. We expand them by C, like all of them get expanded by C. There is no changes at this point. And after that, we want to find all the strings so that we should add epsilons to them. Okay? So basically, we have this new string, and so okay, what are the new suffixes? Okay, so let's consider a suffix here that contains a C, and so the state that it should go to. So we are assuming that, this state was present before, because basically up to this point, the new terminal vertex was the only vertex that we have created. Okay, and we assume that not much happens to all the other vertices. So what we want to find is, for example, what is the smallest suffix of the new string that occurs somewhere else in the old string? Because if a suffix did not occur anywhere, did not occur before, then it's just equivalent to the whole string, right? But it must be other way. So we want to find the largest suffix that occurs somewhere, like this. So the equivalence class of the whole string is the whole string and all the suffixes up to the point where it becomes occurring somewhere. Are there any questions? Okay, so let's try and repeat it. Basically, Yes, so basically we try to group our strings, our substrings by the right context. Okay, so, and we know that the right context looks like this. Up to a certain point, all the suffixes of a particular string. So now what happens is, like when we write a C here, then we know that one new state appears. So basically, first what happens if we introduce new epsilon, the state epsilon, okay, the right context epsilon, and to all other states, the right context, like, okay, so for every string v, what can happen to its right context? So let's write the right context with respect to the string of s plus a character c. Okay, so rc of, with respect to this new string of v, related to the previous right context. So it's basically, we take the previous context of v, then we take all of the strings and append them by c. So we can write it just by this. So this means append all the strings in this set by c. And after that, there are two cases. It is either expanded by the epsilon, or it not expanded by the epsilon. So one of these two cases. All right. So one thing is the number of states can at most double, because the states can only break apart. And the question is, which states do break apart? Okay, because if a state does not break apart, then we don't have to do anything to it. Okay. So let's try and figure out what does it take for a state to fall apart when we add this character here. So after we add this character here, it does fall apart is if, like, some of the smaller suffixes receive epsilon in their right context, which means that if we take this suffix, then it occurs somewhere else. Okay, but the larger things, the larger suffixes do not occur. So yeah, we had this string that is like this suffix appended, like continued by c, and so since these are equivalent, they are equivalent in the original string. Like, I mean, so let's look at here at the state. We have, let's say, smallest suffix and largest suffix. So I don't know, it could be a capital and a small. Okay, so we know that a small gets epsilon in the right context, because we assume that it falls apart, and the larger does not, doesn't get epsilon. But they were still equivalent, right? In the previous string, when we didn't have c. So, okay, if this gets epsilon, then okay, so let's draw our string again. So this was this is a picture of a class, and this is a picture of a string, right? Okay, so if a gets epsilon, then what it means, it first of all, these these suffixes all end by C, because a string gets epsilon only if it's a suffix. So the last, at least the last letter is correct. Okay, so it ends with C, and up to, like, when we didn't have the new letter, they were equivalent. So anytime we had A capital, we also had A small. A capital, A small. But now we have something, and C is at the end. So here is C. But now we add a new character C, and it just so happens that A is here, but A capital is not. So this is the reason why the state will fall apart. Okay, so A capital does not get epsilon because it is not a suffix. Okay, so since both of these suffixes end with C, they have a particular state in the suffix automaton. So they have a state, and it also gets like, let's look at something that, well, we can arrive to this state by the letter C, right? And there can even be multiple states that arrive there with the letter C. Okay. So yeah, so basically the states that arrive here with the letter C, let's take a closer look. So we have the largest A, we have C here, and if we cut that off, we obtain another range of suffixes over smaller strings. But the thing is, they can no longer be, some of them may be non-equivalent. So there can be different states that correspond to these smaller ranges that go into this by appending C. Okay, makes sense? Or yeah, I know it's hard. Okay, so if you think you have a good question, you may help me a lot by asking it. Okay. If not, that's okay. I think I'll just speak for myself, to myself for now. So, why did this fall apart? This fell apart because one of these suffixes, like, we know that it fell apart because A without the last letter was a suffix before, but A capital without the last letter was not a suffix. So it means that out all of these states, some are terminals and some are not terminals, basically. So the smallest of these states had epsilon, but the largest of them had not epsilon. So this is basically the criterion of when the state falls apart. Okay. So now let's try and figure out when that happens. Basically, basically we can do as follows, right? So we only care to look for states that are reachable from terminals in the previous automatons. So basically, we know that the terminals form a chain of suffix links, right? And in the previous automaton, and we know that the states that have a chance to fall apart are the states that reachable by C's here, from these terminals, because we have to have it here. Here a terminal, and here a C. Okay. So one way to go now is to basically go up the chain of terminals and see if there's a transition by C, and then try and figure out what happens here. Okay, so that's the general idea. And well, how do we treat with like basically how do we get around this? So we have to find out about whether this situation is present. Okay. My intuition would be let's see here. Okay, maybe that was too much effort in laying out the proof. I think it's at this point, at least, it's going to be good enough if I just, tell you the algorithm for constructing that. At least the proof goes along these lines, and we're not even starting on, proving the complexity. So what we're doing, so we are going to expand, we are going to add another letter, right? So we had the previous, so what we had is like a bunch of states, a bunch of errors, also a bunch of suffix links, and we know which state was the root and which state was like the final state. So what we're going to do now is we are introducing the new epsilon, like the new final state, uf. And if the new letter is C, then it's pretty obvious, then we have this C here. Because this corresponded to the previously, the string that was previously like the old string. So we have this here. And then we start jumping up by suffix links. Let me just write it down for you. Do I have a lot of time? Or not really? I mean, 30 minutes into the lunch? Oh, 3. Okay. Let me just write it down real quick. Anyway, it will take 5 minutes as long as I do not forget how to go. So we add the new final state, and we add the, so if f was the previous final state, then we go, we should add the edge here by C. Then basically we go like this. We start, so our S is initially F, and so we have to go up we have a C here, and the suffix link must be here. No, okay. So first of all, if there is no transition by C, then we must add this transition here. Okay. So this happens while there is no edge that goes from S using C, and then we go to the suffix link, and then we say that okay, we want to add an edge from S to UF that uses C. So after that we have finally, so either we have arrived to, so this is initial state, so either S is init, in which case we are done, just return. So that means that we have added a new letter, basically. And this is the only thing that we need to do. Otherwise, we have
we have a particular state. Which has C going down. So now actually two things can happen. We also have to store into in our state the length of the largest string in the state. Okay, so it's called len. So basically, what we're going to do now. I'm not quite sure at this point. Okay. Tell you what. Let's try and have some. I will try and have some printouts prepared for you for the contest, so that you can at least study this to a degree. And maybe it's just a waste of time at this point. So yeah, that wasn't too good, I guess. All right. So let's go to the lunch now, and we'll figure something out for the contest. I'm sorry.